All right, here's my project milestone update for CSI 703 Spring 2019. So currently I'm at the point where I've fully defined all my data structures, and I'll get to that in a second. One thing I had to do was do some background research, and I made this whole PowerPoint learning about basically astrophysics and really interesting things here. So I can give this out. I'll bring it with me, but basically I had to do this to understand the data that I'm dealing with, and things like spectral type. How do you encode this data into being able to be processed, right? So there's a lot of really important things that I had to do before I could even get into the data. So with that being said, here's my notebook or my journal. That is a Jupyter notebook, and this is where I'll store everything that I try. So here you can see I'm using Python. Like I said, I plan to use R, and more specifically R2D3, which is something that allows me to use D3 inside R, and I can in turn use that in R Shiny. I think that's the plan for now. So show some visualizations that I have now. So here's the data in its form, and first start off with data cleaning, and here are some of the columns that had more missing than 1/3 of their total values. So out of the 3,900 rows, these had more than 1/3 missing values. So some of these are kind of important though. So I eventually dropped them, and then I decided not to drop them because it reduced too much of the data. So I could look at those pieces alone and just drop the other planets that don't have those data points. Okay. So after playing with the data a little bit, doing some cleaning, I did some exploration. So basically, to understand the spectrum type, I had to do some more research and figure out what spectrum bands they're measuring, because different light different types of frequencies are captured by different devices, and here are there's three different methods. There's Gaia here in green, captures this nanometer range, and then Johnson and 2MASS. So I was going to look into possibly a little bit of classification, categorization concerning these three different spectrum absorption methods. So getting straight into data, I decided to do some just basic exploratory data analysis. This is based on magnitude, the two different types of luminosity. So there's optical magnitude, and then this is near infrared, NIR magnitude. It seems like they're pretty heavily correlated. Going on, I did a little Pearson. This is nothing much. I'm gonna skip on here, but and you can see this notebook is pretty big, so I'm gonna kind of get through this. Let's go ahead. Okay, so the first thing that I really looked at was eccentricity, and once again, I have to do all this exploratory data analysis to figure out my data, and see what I can do with it. So here I looked at eccentricity, and what that is the essentially how stretched out the elliptical orbit of the planet is. Oh yeah, it's up here. So here's eccentricity. So from 0, it's a perfect circle, and higher, up to 1, and you can see the limits here. Up to 1, it's very stretched out. So I was curious about what the different eccentricities are. I found out a lot of them were close to 0. Earth has eccentricity of 0.01067. 0.167, so pretty close to zero. So that was pretty surprising. And then some planets are very much closer to this, the green circle here on that part of the spectrum. So then I looked into how many planets have circular orbit. So this is getting me into my first kind of classification thing. I want to plot these planets against the other planets who don't have a perfectly circular orbit, and see what the different properties against each other might look like mass versus radius. So I made a data frame with circular eccentricities, and I added a column to differentiate them from the others. So here's this little exploration thing I did. Nothing really came of this, but you can see me trying different things here. I do want to make an interactive correlation plot. That is one plan, so here's kind of the foundation for it. But let me move on in the interest of time to more of the other things I've done. Alright, so here's the first kind of testing my experiment. So I looked at stellar mass, which is how many masses of the sun. So here you have like 8 million masses of the sun. And there's one planet, or I mean, this is a star. There's one star that is very close to that. And then planet radius in terms of Earth. And then you could see the clusters here. So the ones with nearly perfect circular orbit, seems like some of them are out there in terms of mass and radius, but the ones which are not circular seem to be all here. Interesting. Then I did a little conversion of that stellar mass into Earth mass, so call that sun to Earth, and then I cut down the boundaries a little bit. So we're looking at inside this box. I want to enlarge this picture a little bit, and here's what you get. So you see kind of two clusters here with the perfectly circular orbit planets seem to be clustered around these 2 points. Interesting. Let's move on. I did a couple more exploratory plots. That's sun to Earth again, and then number of system stars for each planet. How many other stars are in the system? So I was just kind of looking. These are binary systems here under the 2 column. There is a handful of 3 and 4 star systems, like 4 suns in one system. But interestingly enough, there's like only one planet with those systems that have higher stars inside the system. Only one planet usually for those. I also aggregated this host name and number of system stars, so I could figure out how many planets are within each system. So I added that column because I'd like to look at that later. Most of them have one planet, and here's stars on the left and planet on the right here. There's a couple like 2 star, 5 planet. Pretty interesting. So I'd like to look at a visualization with like maybe more than 3 planets and at least 1 star. Like to look at visualization on that later, cut it up. I found nearly 3,000 host planets, or host stars, I guess, and then that's out of 3,900 planets within those host stars. So the ratio is very small, it's nearly 1-to-1 basically. It's pretty close of number of stars to their host to the planets within the system. Let's go ahead and go down here. I did another mass of stars in the system versus number of planets in the system. So you could see here we've got 1, 2, 3, 4, 5, all the way to 8 planets in the system, getting closer to our system. But this is the mass of the stars in terms of Earth masses. So 14 1.4 million. It gets pretty big. I think I even cut it off here too. So this is kind of an interesting trend though, as well. So all things I plan to explore, if it makes sense. So then I get into clustering. First clustering I do is k-mains, of course, and I just assign 4 clusters and I give them black circles. You can see here. But then I do the elbow method. We find 3 is the optimal clusters, and then bam. So this looks a lot better. So this, I eventually don't end up using this for tagging the data, but yeah, I had a DB scan script that worked, but it's not working right now. I did affinity propagation, that did not work whatsoever, and clustering, the DB scan didn't work either, because look at the number of noise, pretty much all noise points. Affinity, that didn't work because 185 clusters, no way. Agglomerative worked pretty well. I really like the cutout here. That's a pretty good clustering that you can actually figure out differences of planets from. So taking that clustering with the 5 clusters there, the next step is to put it against, like a scatter plot with star luminosity versus stellar gravity, something like this. Stellar mass versus stellar luminosity. And that these are in terms of the sun, how many suns in mass and how many suns of luminosity, or however you want to do that. So here's the number of planets per cluster. So it's pretty broken out, but this group is definitely more heavily clustered together, whereas like the purples are out, a little bit out trailing, and same with the greens. So I think it makes sense. The clustering is a good label, definitely a good label. The next thing I went into, I did a little bit more refined clustering with log conversion, because this data is huge. I mean, we're talking like insane masses. Even if it's in terms of Earth's mass, it's still like 1.4 million. So when I turned it into log, here's a cluster I came up with, and this is the one I eventually end up using. So once again, here's those graphs with the clusters, and I decided to use a little circular. I use a package called Circlify, and what I did is I took all the pairs of planet radii and their respective cluster tag, and so as you can see, the 3s are all up in the top, and I took the unique one. So for each cluster and their value pair, then there's going to be the unique pairing there. So here's what it came up with. Here's a little kind of example of what I'm going for. And before I take this to interactive design, I wanted to plot it out first like this and see what it looks like. So you can see the 3, I mean, obviously that's our big group up here, right? 3,300. But what's more interesting is the 2s, 1s, and 0s. That's a 0 cluster. They seem to have all the same size, but the 3s are very distributed, right? So that's interesting, and this is in planet radii. So you could see already 1s, 2s, and 0s are pretty related, and 3s are much bigger, it seems. There's another circular method I was trying to play with right there. And one more thing I did is try to look at a 3D graph of it. Planet mass, planet radius, planet density with the clusterings. And we can go ahead and let me run this. So here you could see a little better. So here I have it planet density cutting off at 1200. You see this guy's an outlier, so I decided to cut off at 200. So let's go down here, planet density. Here it goes up to 140. I did less than 200, so it automatically scaled. And then let's make this marker, since there's so few blues. Let's make it a little bit bigger, so you could see the blues up in there clustered, and then the reds have this zone, and the purples are here. So this tells me purples have more planet density. Interesting, right? And they're also clustered quite around the 5, and planet mass is very small for purples, it seems. There's a green section of clustering over here, very different from everyone else, and the blues are tightly packed too. And then the reds are more over towards low planet mass, high planet radius, pretty much zero density. So that is what I've done up to this point. I do have a lot of future plans, and before I get to all the interactive, I'm just trying to figure everything out in Python, which is my comfort land, and then I think I'm gonna go with R2D3, and if not, I will use HTML widgets and some other nice R packages to create a nice shiny app that you can play with, and similar to the FIFA presentation medium, and you'll be able to play with that and figure out some insights, hopefully, from this project. Thank you.